Thin film coatings are engineered material layers ranging from a few atomic planes to several micrometers in thickness, deposited onto substrates to modify surface properties without altering the bulk. Because surface characteristics determine adhesion, friction, optical performance, corrosion resistance, and electronic behavior, thin films allow the design of components with tailored functionalities. They can be amorphous, polycrystalline, epitaxial, or layered superlattices, with performance depending on composition, microstructure, stress, and interface quality. Deposition methods include physical techniques such as evaporation, sputtering, pulsed laser deposition, and molecular beam epitaxy, as well as chemical approaches like chemical vapor deposition, atomic layer deposition, and sol-gel or solution-based methods. Each technique offers different levels of control over thickness, uniformity, and conformality, making them suitable for specific industrial and scientific needs. In optics, thin films are crucial for controlling light. Anti-reflection coatings on lenses and solar panels use combinations of oxides like CO2, MgF2, Al2O3, and TO2. Dielectric mirrors and optical filters rely on precisely engineered multi-layers. Transparent conductive oxides such as indium tin oxide and aluminum-doped zinc oxide combine transparency with conductivity for displays, touchscreens, and solar cells. Low emissivity coatings on architectural glass use nanometric silver films to minimize infrared heat loss. Electronics heavily rely on thin films for semiconductors, dielectrics, and interconnects. Gate oxides have evolved from CO2 to high-K materials like Fo2 to reduce leakage in nanoscale devices. Conductive interconnects use copper with barrier layers like tin or tan. Thin film transistors made of amorphous silicon, IGZO, and GaN power large-area electronics. Magnetic films such as permalloy or CoFEB enable memory devices and hard drives, while superconducting films like NBN and IGO are vital for quantum circuits and photon detectors. Energy applications are equally important. Photovoltaic technologies such as CDTA, CIGS, and perovskites use thin film absorbers optimized for light harvesting and defect control. Thermoelectric devices employ Bi2Ta3 and Sb2Ta3 thin films, while batteries benefit from ultra-thin coatings that stabilize electrodes and solid electrolytes like LiPo for microbatteries. Mechanical and protective uses include hard, wear-resistant, and low-friction coatings. Transition metal nitrides like tin and CRN extend tool lifetimes, while diamond-like carbon and MOS2 provide lubrication. Thin oxide and nitride layers also act as moisture and oxygen barriers for electronics and packaging. In biomedical applications, films enhance biocompatibility, osseointegration, and antimicrobial performance. Tin and DLC are used on implants. Hydroxyapatite encourages bone growth, and silver-containing films inhibit bacteria. Functional organic monolayers tune surface chemistry for sensors and lab-on-chip devices. Piezoelectric and ferroelectric films such as ALN, ZNO, and PZT are used in actuators and MEMS, while 2D materials like graphene and MOS2 enable ultra-thin electronics and detectors. Characterization tools such as ellipsometry, X-ray diffraction, electron microscopy, and atomic force microscopy are used to probe thickness, structure, and defects. Ensuring adhesion, minimizing stress, and preventing diffusion or degradation are key for reliable performance. Overall, thin film coatings represent a versatile class of materials that underpin technologies from optics and electronics to energy, aerospace, and biomedicine. Their power lies in the ability to engineer nanoscale structures and interfaces with precision, enabling novel physical effects and superior device performance.